Anyway, my point is that to actually carry out this limiting procedure for a specific example is rather nuanced, isn't it? And it wouldn't be that hard. Like, this only works in as much as what? We have Gauss's formulas, right? Without Gauss's formulas, we wouldn't be able to carry out this program of calculation, right? So Gauss's formulas are integral in the logical sense of doing this integral. But this is probably the only Riemann integral. By the way, this is called a Riemann integral. Technically speaking, the Riemann integral is something a little bit more cagey. It doesn't, I'm just using the right endpoint rule to calculate the integral because it's convenient. The Riemann integral actually allows us to use any approximating scheme to calculate the area. Anyway, so listen, like, the proper statement of integration is technical. I'm trying to give you a honest but not general presentation of it, okay? Well, computer. My brother made a website where you can visualize left and right and midpoint rules and then other more exotic things for a given set of example functions. And also, I think you can put a formula in as well. Let's see if I can find it. Let's see here. Oh, yes, my art. Come on. No, I don't want to restore pages. Let us find. So here's how you can find it in the Google. Bill Cook Math Sage Interaction. And let's just try that. Bill Cook Math Sage. So here's billcookmath.com, which is my brother's website. My brother's a mathematician at Appalachian State. I guess I probably should move the camera, huh? Duh. All right, so if I was supposed to give you guys a quiz today, I'm sorry, I forgot. Was I supposed to?
No, we had a test last week.
Oh yeah, okay. So I get a break, right? Yeah. I do have a quiz. I do have the test to get back to you guys. Don't let me leave without doing that. Let's see here. Let's wrap this up here. Oh, come, no, what? Don't. You teams. I tell you what now. All right. No. I do not consent. I do not consent to teams. Let's see here. All right. Come on. Rats. Calculus. We want the calculus demos, right? All right, so my brother has a number of calculus demos. The one we're interested in is area approximation. This will compute. So as you can see, my brother, whoa, what's going on with that? Dudes, look at that. What? Well, here, let me fix it. There we go. Now we're good. As you can see, he's got the formulas for the left, the right, and here's the midpoint rule formula. Something else called trapezoid and Simpson's rule. Trapezoid approximates the area by using trapezoids. Oh yeah, trapezoid and Simpson's rule. Numerical calculators are usually based on Simpson's rule. But here's a picture. So his token example is e to the, oh man, that is really annoying. All right, let me, just a second here. I can play this game. There we go. Come on. Come back to me, little arrow. All right. All right, so this is, so as you can see, his website calculates the left, the right, the midpoint rule, the trapezoid rule and Simpson's rule and tells you the error in each for this particular function. And you can change the a and the b. Let's try to do one we just did. We had what? X squared, right? And we did 0 to 2, didn't we? All right. So there you go. That's the left endpoint rule was 7. The right endpoint rule was 7, right? And what we're showing right now is what's being visualized. Midpoint rule is being visualized. What would the left-hand rule look like? There's the left endpoint rule. Oh, let's not do both at the same time. So there's the left endpoint rule. Here's the right endpoint rule. As you can see, the right endpoint rule is an over approximation, whereas left is an under approximation. You probably want to see the Simpson's rule, trapezoid rule, right? Here's trapezoid rule. So you can see that the trapezoid rule it's so close. It's right, yeah. I would say that's not actually about math. That was sports related, wasn't it?
I was playing Clash Royale. I won at the last second. Exactly marble.
Oh, you're playing. What were you playing?
Clash Royale.
Oh, Clash Royale. Yeah. See, that's I'm not. I tried to play that. I just couldn't get into it. Simpson's rule uses approximating parabolas for each subsection. All right. Anyway. So I think this is kind of fun. All right, so let's take the last 5 minutes of class here. Give me a second, and I will hand the test back for you guys. Let's look at the solution together for a minute or two. If I can find it. I think I scanned the solution. I don't think I've posted the solution yet, but let me talk about it momentarily. Any A's on the test? I mean, all right. Here we go. So, I think I could say, I think all of you are studying. That's good. Many of you have considerably more studying to do. You're not where you want to be yet, right? Now I do think some people got problem 1 right. So the scores are not visible, so you guys can just take yours and pass it out back to back. So here, I'll speed this process up a little bit.
Okay.
There you go. Here you go. Here you go. Uh-huh. There's no telling if I have. Oh, I do have yours. So what do you know? And if I had, no, yours is in the other stack. Christopher, yours is here. I took it from you. There you go. Josh. All right, so excuse me. So I will. Here, I'll take it. You're fine. I'll post. Everybody get theirs? Did everybody get them? Everybody got them? Okay, so. All right. I'll be very quick. Here's problem 1. The answers were 2 and 3. Here, the graph looks something like that. You don't have to graph negative. I just said x is greater than or equal to 0. The maximum force happened to be at 1/3. For problem 3, there were critical points at -2 and -3. And so you have increase -infinity to -3 and also -2 to infinity. And it's decreasing from -3 to 2. F of -2 is the local min. F of -3 is the local max by first derivative test. This was a homework problem. Not the same, but there is a homework problem just like this. So more of you should have gotten this. Many of you did not. But I thought that would happen. That's why I only made it worth 5 points. I was trying to be nice. But you know, you do need to like understand homework problems. Concave up, concave down, we look at the second derivative. Some of you are wrong, I think probably because you're looking at the first derivative. 0 is not an inflection point. Just because the second derivative is 0 doesn't make it an inflection point. Inflection point is where the concavity changes. The concavity does not change at 0, therefore 0 is not a point of inflection. That's why I try to say f prime prime of x gives us possible points of inflection. For problem 6, 1 is the only critical number. The inflection points happen at 1 plus or minus the square 1 over root 2, which you could write other ways, but that's one way to write it. The graph looks something kind of sort of like that. You could use, I should mention, in this other problem, the first problem, first page, L'Hopital's rule tells you that the limit as x goes to infinity is 0. Let's see here, I guess we're out of time. But this problem here, you know, I think everybody can study this problem 7, see if you can't get it right if I put it on the final, okay? Like, I think everybody can get this, but you need to be more confident about what you're doing and like not give up I don't know, there's like, I'm not sure what happened there, but neither 1 nor 3 are critical points here because they're not in the domain of the function. Those are critical numbers, but not critical points because those are where vertical asymptotes are. And then here's the L'Hopital problems. I didn't mean for this to be tricky, but notice I should have put like square root of pi to make it L'Hopitalable. As it stands, it's just plug in pi squared, and it's just continuous there. You just plug it in. Because pi squared doesn't make that have division by 0. So sorry, I wasn't trying to be tricky there, but you know, I did give significant partial credit if it looked like you did L'Hopital's rule correctly, but you know, illogically. And let's see here, what else? So yeah, I'm sorry, I didn't mean to look at that last page. So, well, I just don't want to talk about it right now. Anyway, we're out of time, so I should shut up. So, sorry guys, see you tomorrow. Oh man, sorry guys. Thank you. I was just going to say the last problem is tricky.